Okay, so today is basically the last material that will be on the exam on Friday. And I think you're going to find today's material less taxing just because from a theoretical standpoint, it's just not abstract. It's not very complicated. And so we're going to get right into it. There are some very specific types of problems they're very interesting and they're kind of fun and fairly simple to manipulate. And it has to do with the modulo or the mod. Now, a couple weeks ago, I talked about clock arithmetic. Now, right now, let's say it's exactly 8 o'clock. Let's just make it easy on ourselves. So right now it's exactly 8 o'clock. In 3 hours, it's 11 o'clock. Now, don't think military time. I don't want to go there. I'm saying you're looking at a digital display, okay? What time is it in 6 hours? Right now it's 8 o'clock. In 6 hours, it's not 14 o'clock. What time is it?
2.
It's
2 p.m.
It's 2 o'clock. Yeah, not AM PM, but it's 2 o'clock. So what is it in 12 hours from now? It's 8 o'clock. What is it in 23 hours?
7.
So you have to think about it, but isn't your answer always going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or 11, or 12? And then it just keeps recycling and recycling and recycling over and over and over again. That's called modular arithmetic. I like to say clock arithmetic, but it's not exactly the same because in the clock arithmetic, I can't actually have a 0. 12 o'clock is sort of technically the 0. But the idea as I recycle, I keep getting the same things. So if I was talking about possible remainders, okay, let's keep it really simple. All right. I have, let's say, 3 divides x, where x is an element of the integers. And x could be any integer. If I said the statement 3 divides x, then we know that x is equal to 3 times t for some t in the integers. We know that's true. Okay, great. That means x is a multiple of 3. But what does it mean to be a multiple of 3? It means that if I divide it by 3, I get a remainder of what? This is the key.
0.
I get a remainder of 0, and that's critical. Will all integers, and we're only talking integers, we're not talking real numbers. Will all integers have a remainder of 0 when I divide them by 3?
No.
What are my possible remainders when I divide by 3? You have to think about this for a minute.
Either 1 or 2.
Yeah, because if I said 2 divided by 3, well, that is just 2. But what about 7 divided by 3? I don't say it goes in once with the remainder 4, because remember the rules about remainder? What was the rule about remainder? Do you remember?
Can't be greater than I forgot the exact, the 3. Can't be greater than the 3.
So we said, dq plus r, and r was limited to what? R was between, remember that? You could go up to, but not including. Oh, that's okay. So if 3 is my divisor, that's why we call it D for divisor. And I said 7 divided by 3. We say the answer is 2 with the remainder of 1. We don't say the answer is 1 with the remainder of 4 because 4 is bigger than the divisor. So the rule of thumb on the divisor is that's not the upper limit. It's 1 less than the divisor's upper limit. So if I was dividing integers by 3, we agreed then my possible remainders would be 0, 1, or 2. Is everybody cool with that? That's a fairly simple notion. Well, that creates an entire equivalence class of numbers. We talked about reflexive, symmetric, and transitive yesterday. So I'm going to introduce new notation, okay? So if I said I'm thinking of, let's say integers, and the way we want to say it, we call them equivalence classes. Equivalence classes are the set of integers that have the same remainder, because then they would be reflexive, symmetric, and transitive. So if I started off with something as simple as modulo 3, we could do modulo 2, modulo 7. It does, we'll do a whole bunch. So if I just said the equivalence classes modulo 3, then that means my possible remainders are 0, 1, or 2. I think we all agree with that. That's a fairly simple thing. So what numbers would be in the same class? Now, here's the crazy part. It's the way we represent it. So if I said, for example, if I said and we write a rectangular bracket, this is in a particular equivalence class. This represents an infinite number of values, all of which that will have the same remainder. Okay. Now, the number 2, when I'm dividing by 3, obviously has a remainder of 2. Oh, okay, because I get 0 plus 2. Can you think of another number that has remainder 2? I'm just writing out. What's another number that would have remainder 2 if I divide it by 3? It's a fairly simple notion.
5.
Can
8.
Do you agree that I could do this forever? Right? Like Captain America says, I can do this all day. Do you agree with that? How about if I went the other way? Would that work also? Because I didn't say the numbers had to be positive. I just said they had to be integers. Would all of these numbers, when divided by 3, have the same remainder?
I don't think -1 or the negatives would.
Are you sure? Because you had a question.
Oh, wait, never mind. Yes, they would.
Yeah, I can do that. Remember, the remainder has to just be a positive number. Yeah, I made it easier by counting by 3s. So simple question. Can you write -4 as something times 3 plus a positive number? Can you write that as something times 3 plus a positive number?
Yes.
What would you write it as?
-2 plus 2.
-2 times 3 plus positive 2. Do you all agree with that statement? The key is this has got to be positive, and we said it's got to be one of these. Okay, so the number -4 does belong in this set of numbers. So that part's fairly simple to see. So in simple arithmetic terms, if I said -4 mod 3, you would tell me that equals 2. Do you remember this math? We did this before. The mod is the same as asking what is the remainder. If I said -4 div 3, what's the answer? It's up there somewhere.
2.
It would be
-1 or
-2, sorry.
-2.
It'd be that number. Div and mod are completely different. I mean, I could come up with a number where they're the same, but that's just coincidental. So what we're looking at today, this is our goal today, is the mod part, not the div. It's all about remainders. So this here says all of the numbers, every integer that exists that has a remainder of 2 is in that equivalence class. It's that simple. So if I said -4 mod 3 is 2, and I said, how about 8 mod 3? What is that? Trying to
2.
make. That's also 2. Oh, so this and this are actually in the same equivalence classes. And here's how we can write it, believe it or not. We'd say the equivalence class that I'm going to say is that, now that means I'm counting by 3s forever, is equal to that one. Whoa. And they're both equal to this one. There's an infinite number of ways of describing an equivalence class, and all you have to do is represent one value in that equivalence class. By the way, I have to give you the original instruction. I actually have to say the modulo 3 before we start this problem. Therefore, the infinite set of numbers that are in this class are the same set of numbers that are in this class, and they're the same set of numbers that are in this class. So there are an infinite number of representations of the same equivalence class. Whoa, isn't that crazy? Isn't that absolutely wild? So let's try another one. Let's say we're talking about equivalence class this time, and I want to use modulo 5. So equivalence classes modulo 5. So the first thing is true or false I'm gonna put a question mark. For equivalence classes modulo 5, is this a true or a false statement? And we're going to be able to show it mathematically. This is not a guess. So for it to be true, what would have to be true?
The remainder supposed to be equal.
They would have to have equal remainders. Perfect. So what is 14 mod 5? What is 31 mod 5? Now you can do this in your head. You can do this using a calculator. How do you do it using a calculator? What would you be looking for in the calculator?
Just you divide 31 by 5 and the nearest whole number, like the whole number, you divide that by or multiply by 5 again.
Yeah,
See what the difference is.
There's actually, if you have a cheap calculator, I'm sure this is actually not very hard to do. So I'm going to use my fraction key, 31 fraction 5. Okay. Equals, and what does my screen say? Does anybody know how to read that screen? I just used my fraction key. It says 6 1/5. That's how you read that. That's really practical, isn't it? 6 1/5. So my div would be 6 and my mod would be
1.
1. That's it. Yeah, your fraction key on your calculator is actually programmed for div and mod. People don't realize that it is. Oh, okay. So what did I entered 31? So I can say 31 is, we just did this, 6 times 5 plus 1. I can say 14 is 2 times 5 plus 4. Okay, I know that's true, and I could have just done that on my calculator. So the question is, what is 14 mod 5? What is 31 mod 5? So whether you do this first or you do this first, it doesn't really matter. Either way, what's 14 mod 5?
4.
4, and 31 mod 5 is
1.
1. Therefore, the answer would be not equal. That's it. I'm comparing remainders. So as a very, very simple exercise, if I gave you a number and I asked you what the mod was, you could tell me. If I said, are these equivalence classes equal? You can tell me. So now let's have some fun. Let's continue. We're working mod 5. Excuse me. And I'm going to give you a whole set of equivalence classes. We're mod 5. Now, remember, it's the rectangular brackets. Make sure I can read it's rectangular brackets. I have the following mod 5. Okay. 7, 11, -4, -8, 0, 13, 21, -6, 17, 19, and -5. Here are what I give you: 2, 4, 6, 8, 10. I gave you 11 statements. How many possible equivalence classes are distinct if I'm doing modulo 5? How many distinct equivalence classes would there be? That's not a trick
4.
question. Careful.
5.
You have to be 5, because what are my possible remainders?
0, 1, 2, 3,
0,
4.
1, 2, 3.
Yeah.
Oh yeah, well, we forget the 0. Oh, okay. So if I'm dividing an integer by 5, I can get 0, 1, 2, 3, or 4 as a remainder. And by the way, when I get 0 as a remainder, that's the definition of divisibility, but that doesn't change this process. So what I'd like you to do is just take a moment, and I'd like you to put these together. There are at most 5 distinct equivalence classes. So put the ones that go together. It's a simple exercise. Okay. So I want you to try that on your own for a moment. Now, it doesn't matter what order you do things. It doesn't matter how you look at them. You might say, let me start by doing all the ones that have a 0. Let me start. I can do it that way. That's fine. An easy way to do it is pick any one of them and just count by 5s. That's another way to go. Okay. I kind of want to leave them in the order I have. So Are there any that are equivalent to 7? Are there any up here that are equivalent to 7?
No.
-8.
-8
Oh, -8. Yeah.
and
17.
17. Good. Okay, that's it. Comma. That's one set. Now I'll just move to 8. I'll just move to 11. I'm going to be lazy. I could rearrange these, order them. That's just extra work that doesn't really get me an answer any faster. This pen is starting to die. Ooh, all my black pens are starting to die. Hold on a second. I have more black pens here. Yeah, here's a good one. All right. So are there any that are equivalent to 11?
-4.
-4. Ooh, look at that.
21.
Beautiful. And we got to 21. The negatives throw us sometimes, but some of you figured this out really quickly. There is a really simple way to proceed. That would be good. I think that's it. Now, I haven't used -4. Yes, I have. I have used -8. So let's go with 0 as the next one. Are there any that are equivalent to 0? So 0 would be all the numbers that are evenly divisible by 5. That would probably be the easiest set to identify. Is there anything up here?
It would just be 0 and -5.
-5, good. All right. Have we used 13? No, we haven't. So how about 13? Did we use 13 yet? No, we didn't. I had to do a double take there. So is there anything that is equivalent to 13? Or is it its own class?
I think it's just its own class.
It's its own class. I think you're right. And then what's left? Have we used 21? Have we used -6? We have not used -6. Is anything equivalent to -6?
19.
19. Anything else? Or are we done?
That'll be it.
How do you know we're done without doing any more work? We are done.
Can you just see all the ones under the line, or?
Yeah, we probably would have been wise checking them off as we went. We didn't, but we probably would have been wise. Do you see any repeats? No. There were 11 classes to begin with. I have 11 classes up here. I'm pretty sure we covered all bases. Was that a hard thing to do? No, it's just identification. That's actually something that should feel really, really simple. Now, what makes them equal? So how can I say -6 is equal to 19? No, that's not what we're saying. We're saying the set of all integers that have the same remainder as -6 when divided by 5. That's what we're saying. So if I took the number -6 and I counted by 5s in either direction, whatever number I produce would be an equivalent class to that one. And it would also be every number. So this represents every integer. So counting by 5s in every direction, I would have equivalence classes. So that's a pretty simple notion if you think about it. Okay, that's just not very complicated. Now, excuse me. The div and the mod, again, are considered just really important operations. But today we are concentrating on the mod, not on the div, like I said before. So I'm going to now give you another set of questions, and I'm going to ask you yes or no, true or false. Are they equal or are they not equal? We just did one a moment ago, but now I'm going to do it not as equivalence classes. If I said the following, mod 2, mod 3, okay? Mod 2 mod 3. Are either one of these statements true? Are either one of these statements true? Anybody want to try that?
The one on the left is.
The first one is, and the second one is, or the second one is not?
The second one is not.
Okay, good. So the first thing is, I gave you the same equivalence classes. I gave you different mods. There's no way they could both be true. Okay, first of all, they couldn't both be true. It's that simple. So how come the first one is? Because if I said, what is 5 mod 2, you would tell me the answer is 1. What is 7 mod 2? That also is 1. Over here, 5 mod 3 would be 2. 7 mod 3 would be 1. Oh, because I have different remainders because I'd have a different denominator. Okay, so everybody's cool with that. There's nothing complicated about that. So a way that I could express that really simply is here I would say 5 is equal to 7. Oops. If I did mod 2. This statement is a true statement because these two statements simultaneously are both true. So we can actually say it like this. The equivalence class of 5 is equal to the equivalence class of 7. If I told you originally it's mod 2, or I can say 5 equals 7 mod if I do mod 2, because in both cases, 5 mod 2, 7 mod 2. So that statement and that statement, we can summarize with that statement. Does that make sense? I'm giving you the notation. It's really notation out of convenience. It's a shortcut. So over here, we said that 5 was not equal to 7 when it was mod 3. Okay, so let me give you a few then. Again, this is just an exercise, and there's absolutely nothing that should truly, strain your brains and things like that. All right. 9 equals 36. This is one that I haven't used so far. Okay. Each one of these statements is either true or it is false. So I could answer the question by putting a not equal or just the words true and false. Okay. How are we going to figure that out? Well, the easiest way is to do what's 9 mod 4, what's 36 mod 4. They're either the same or they're not. That's actually the easiest way to do it because that's what we're comparing. So, anybody want to try it? What do they think the first one is?
False.
Because
4 goes in 9 times.
9 mod 4 is
1,
and 36 mod 4 is
0.
okay. That's yeah. Don't go any further because tendency if we go further, we might say something that's whacked. All right. True or false?
True.
True. Ooh. This one might be a little trickier because we've got that negative in there. 8 mod 5 is
3.
17 mod 5. Can you write 17 in div mod form?
-4 times 5.
Perfect.
That's 3.
You have to be able to do this at some point. We've done, by the way, we've done that before. That's not new material, but the negatives always throw us because for some reason we want to get a negative remainder. We want to apply different rules, right? Next one, true or false?
False.
False. Because -2 mod 3, that's a tricky one. -2 mod 3.
Be 1.
So -2 mod 3 is actually +1. It's not 2. That would be a common mistake. And what's 21 mod 3?
0.
0.
Yeah, because 3 goes in. That's, by the way, whenever it's 0, that's supposed to be easy because it goes in that many times. And the last one?
True.
because 5 mod 7, ooh, 5 smaller than 7. Can I do 5 mod 7?
It just
Yes.
equals 5.
I asked this question on the first exam, and believe it or not, most people actually got the wrong answer when I took a number that was smaller than it. So in other words, 5 div 7 is 0, 5 mod 7 is 5. But when I asked questions of that nature on the first exam, it was missed very, very often because we were often thinking of something else. Now that we finished this, does anybody see a shortcut? Does anybody see a way of doing this that would have required next to no work? Well, okay, some work, but not very much work. It actually has everything to do with equivalence classes. Okay, so if I just said, let's keep it really simple. I want to do mod 3. Okay, and let's say the equivalence class we're doing is the number 2. That means all the numbers that have a remainder of 2. So for X to be an element of, X and Y are elements of this. What does that mean to you in simple English? That means that X mod 3 is 2, Y mod 3 is 2. Does that make sense so far if I said that? What else can I say with that? Then that means that there exists an R and an S in integers such that what? X equals 3 times R plus 2, Y equals 3 times S plus 2. Is that also a true statement?
Yes.
So I'm going to give you the, I'm going to run out of room. I'm going to put it up here. Sorry. So therefore, if I said, tell me about X minus Y, but it doesn't matter what order I subtract. What is X minus Y? So 3R plus 2 minus 3S plus 2. Won't that be 3R minus 3S, or 3 times R minus S, or 3 times T if I let T equal R minus S? T is an integer because integer addition and multiplication is closed, yada, yada, yada. So what am I saying? I'm now saying X minus Y is a multiple of 3. X minus Y divided by 3 has no remainder. X minus Y is a multiple of 3 if X and Y are both in the same class. By the way, it wouldn't have mattered if I picked 2, if I had picked 1, if I had picked 0. When you take 2 numbers from the same equivalence class, whatever you're doing the mod, and you take the difference of those 2 numbers, I just proved it, they have to be a multiple of that mod. The difference between X and Y has to be a multiple of 3 if X and Y were both in the same equivalence class. Does anybody see the clear shortcut then?
You subtract the mod that you're looking for and then divide it by 3, maybe?
Not, well, for example, this one, I erased it. What was this? This was mod. What was my third one? It was mod what? Sorry.
3.
This was mod 3?
Yes, mod 3.
Okay. So take the difference of -2 and 21. Does it matter which order you subtract? No. So most of you would probably go bigger minus smaller, just easier. 21 minus -2 is 23. Is 23 a multiple of 3? No. So that one was false. 8 minus -7. This was mod 5, by the way. I remember that. 8 minus -17 is 25. Is 25 a multiple of 5? Yes, it is. And by the way, you said this answer was true. 40 minus 5 is 35. Is 35 a multiple of 7? Yes, it is. And you said this answer was true. That's the shortcut. Because I just proved it here for 3. But in general, given a class mod, whatever it is, we're going to use mods that are single digit numbers. There's no point in doing humongous numbers. This makes it complicated. So I pick a number, mod 3, mod 5, mod 7, mod 13, mod 8, doesn't matter. Now I take 2 numbers from the same equivalence class. That means they have the same remainder when divided by that number. Then their difference has to be an even multiple of whatever the mod was. Okay, no exception. Oh, okay, so if I think of all the numbers with 3 in the denominator, right? Okay, so all the things that have remainder 2, then basically 2 would be the first positive integer that has remainder 2 mod 3. Now count by threes, 2, 5, 8, 11, all of these numbers will have remainder 2. But I'm counting by threes, so their difference will always be a multiple of 3s. Like, oh, right? That's a really, really simple way to view this. That's why this type of math really should never trouble us. Now, the last thing we're going to do, this is literally the last thing we're going to do for the exam, is we're now going to go back to the Euclidean algorithm, which, you know, let's face it, when you were in pre-algebra, actually not in pre-algebra, my youngest son told me he learned to do this in, not the algorithm, but the GCDs in 5th grade. I corrected him. He actually learned to do it in either 3rd or 4th grade because I remember helping him on his homework. To find the greatest common divisor of 2 integers is something you learn years before you even take pre-algebra. That wasn't the point of those problems. The point of those problems was you're actually basically writing a computer algorithm. The GCD is a computer algorithm that says this GCD is equal to this one is equal to this one and so on. But now that we've got that, what if we wanted to work backwards? And what I mean by working backwards, I'm going to give you a really simple example. Okay. Oops. I got a lot of papers here. Let's suppose, excuse me. Okay. I've got, okay, A is greater than B. We know that the GCD of A and B equals the GCD of B and A mod B. That's the computer algorithm, by the way. That's it. That's it. That's all I ever showed you. You do this until you get something of the form GCD of, let's call it, we haven't used the letter C. At some point, you get a statement that looks like this for a positive integer C, in which case that's the answer. Because when I do this, it means I have no remainder. So that means it went in an even number of times. Okay, that was the algorithm to do that. But what if? Okay, so let's say my answer is C. I would like to write A and, sorry, how do I want? I'm sorry, I want to write, not A and B. I want to write the GCD of A and B, sorry. A and B as a linear combination of A and B. Now that's a term that some of you may not be familiar with. If you've had linear algebra, that's an everyday term. A linear combination means scalar multiples. So for example, if I take, let's say X and Y are just 2 real numbers, then 3X minus 4Y is a linear combination of X and Y. Okay, a linear combination of X and Y. 3X squared minus 4Y cubed is not a linear combination. Linear, right? Think like as in line, quite literally. Oh, I can only take scalar multiples. I can't have exponents. I can't have functions. I can't have square roots. I can't have quotients and so on. So when we say linear combination, we're saying I'm looking for coefficients. I'm trying to figure out the coefficients. So what I want to be able to do, if the answer was C, then what we're trying to do is find the specific, let's call it S and T. That means there exists S and T in the set of integers. And by the way, not positive or negative. S and T can be either sign. In fact, what you're going to find is absolutely one of them has to be negative. Otherwise, this isn't going to work. Such that C equals, okay, A was a constant, so A times S plus B times T. Now, of the S and the T that we're going to calculate, one of them would have to be negative. How come? Think of A and B are probably large numbers. If S and T were both positive, then I have positive number times large number plus positive number times large number equals tiny little GCD. Probably not the case. All right. So our goal now is to do a linear combination, and I'm going to walk you through it. Now, the algorithm produces the GCD. What I'm going to show you is the algebra to work backward to generate the linear combination. Now, the algebra it actually is a unique process, meaning if 1,000 people are doing the same problem, they actually have to have all of the same numbers at the same place. There aren't variations. There's no creativity in this case. You're basically just doing a search and rescue to find your numbers. All right. So I'm going to walk you through, because again, it's a fairly simple process, but it's not intuitively obvious before you do it. After you do it, it's fairly simple. Okay. Let me use a pen with some good ink. So I want to find, let's say, here's my instruction. Write the GCD of the numbers 93 and 33 as a linear combination of 93 and 33. So my answer is whatever the GCD is, it equals some integer times 93 plus a different integer times, or another integer times 33. That's it. Okay, that's the process. So first, we have to actually find the GCD. That's step number one. So the GCD of 93 and 33. Well, let's see. Oops. See if we remember how to do this. Well, it's definitely 33, and what would the mod be? 33 goes into 93 2 times with the remainder of what? Anybody? Again, you can use your calculator.
27.
27.
Yeah, that you can't afford a wrong number here because it's too easy to do on any cheap calculator will do this. Then this is going to be the GCD of 27, and 27 goes into 33 once with the remainder of
6.
6. 6 goes into 27. How many times? Like 4 times.
4 times.
With the remainder of
3.
3. I'm gonna run out of room. And that goes, well, 3 goes into 6 exactly 2 times with the remainder of
0.
0. Therefore, the answer is 3. Okay, this is the algorithm. That's what it is. This is not new. This is maybe a little bit of rust. Most people had an easy time with this. Some folks did it completely different than this, which I really can't figure out why, because this is really, really simple. And it's been around for actually several hundred years. Now, by the way, this is not very useful if you have more than 2 numbers. This is only good for 2 numbers, not for multiple numbers. Now we want to work backward, and I'm going to walk you through the working backward process. So now what I'm going to do is I'm going to go back and revisit all my divs and mods in a sense. Okay, this was sort of like the scratch work to start the problem. Now, I want to write 93 in div mod terms with 33. So it's 33 times what? We said it goes in 2 times with the remainder of 27. Agreed? Everybody okay with that? But in the next step, I have a 27. So what I want to do is rewrite this as 27 equals, because that's the next number in the process. So what does 27 equal then? 27 equals 93 minus. Now, it doesn't matter if you said 2 times 33 or 33 times 2. It's going to be the same thing. At some point, you might rearrange things. Okay, so that's step number 1. I take that statement, write it in div mod form, right? 33 times the div plus the mod, take the mod and then rewrite it. Boom, okay, leave that alone. Now we'll go to the next number in the sequence, which would be 33. Now I'm dealing with 33 and 27. So I want to write that guy as 33 is 27 times 1 plus 6. So in this case, my remainder is 6. So this implies that 6 equals 33 minus 27 times 1. Okay, now what? Well, I've already said that 27. So see that there? I'm going to replace this 27 with this. This is the key step now. So if I replace 27 with this, that means this is 33 minus what? 93 minus 33 times 2 times 1. Okay, and now what have I got? I now have, excuse me. So at this point here, I've got 33 minus 27 times 1. Oh, actually, you know what? I'm getting ahead of myself. Hold on. I just realized that's the next line. I'm not there yet. Yeah, I'll just leave this like this. Sorry, we're gonna substitute back in, but not yet. So now the next number is 27. Sorry, I'm getting excited here. 27, and what am I looking at? How many times does 6 go in? So 27 is 6 times 4 plus 3. That gives me 3 equals 27 minus 6 times 4. Okay, we're almost done. Okay, the next number after 27 is 6. 6 equals, and now I'm doing it with 3. So what does 6 equal? It equals 3 times 2 plus 0. I have no more remainder. So this part of the process is finished. I'm not going to write 0 equals. Okay. Now what we want to do is work backwards. And I'm going to start with the last statement I had, which was 3 equals. I'll use a different colored pen now so you can keep track. This is having, oh, hold on a second. My blues have any juice. My blues are starting to die. All right. So 3 equals, go back to the statement here. 27 minus 6 times 4. Okay. But what did 6 equal? 6 equaled this. So 27 minus 6 times 4, I'm going to rewrite that as 27 minus this quantity, 33 minus 27 times 1 times 4. Okay, everybody see that? I'm just copying the previous line. Now gather the 27s and the 33s. Minus, so that would be plus 4 times 27. So I now have 5 times 27 minus 4 times 33. Everybody catch that? Now, I may have made an arithmetic error.
Hey, can you, where did you get the 5 times 27?
4. If you multiply the 4 in there, you have 4 times 1. See that 4 there? We don't want to lose that 4. So I have,
Right,
I have minus 27 times 1 times 4. So that's plus 4 27s.
so what's the 5 times 27?
Because you have 1 here.
Oh, because got it. Okay.
You're gathering your 27s and your 33s. Now, this is the most important part right now of the entire process. Check your work. Believe it or not, I'm going to show you an algorithm that is arithmetic, low-level arithmetic, no calculator required. And most of the answers I get will be incorrect because people don't do the simplest part of all. Check. What am I checking? Multiply that out right there. 5 times 27 minus 4 times 33 equals 3. Good. I haven't messed it up because it's supposed to equal 3. But if I do a bad job of my distributing and gathering, I will have an incorrect value, which means that everything I write after this will just get further and further away. It won't come back and save me. Okay. Now I'm going to go from this part here, and now I'm going to replace what? I'm now going to replace 27 because that was the next number in the process. So I'm going to replace the 27 with what? With that. So I now have 5 times 93 minus 33 times 2. I said it didn't matter what order you write them, because in the end, you're probably going to put your coefficients in front. Minus 4 times 33. Now I have 93s and 33s, which was my original goal, by the way. Okay, so how many 93s do I have? Looks like I just have 5. So I have 5 times 93. 5 times negative 33 times 2. So that's negative 10. Agreed? That's negative 10 33s. Minus 4 more 33s is what? Okay, does everyone see that? I have 5 93s minus 14 33s, and now I'm going to check it with my calculator again. 5 times 93 minus 14 times 33, and once again, that equals 3. So I know I haven't made a mistake. Am I done with the problem at this point? Anybody want to tell me? Am I done?
Yes.
That was my GCF. These were my 2 original numbers. Those are the 2 coefficients. I'm now finished. So therefore, what is the answer to the problem? The answer to the problem is that, oh, I'll just write it next to it. The answer to the problem is 3 equals 5 times 93 minus 14 times 33. There's no way you could look at the original and come up with that. So we find the GCF first, but it's the process. Now, could you just jump right into the middle? Yeah, you probably could. But this is one where you want to write things down and have kind of a paper trail, because if there's an error, you're never going to find it if you don't have something written down. So all I did now was I did every single one in div mod form until I got a 0 remainder. I wrote the remainder as the quantities in reverse. So in each case, until I got a 0 remainder, I wrote them in reverse. Because then when I start at the end, I'm going to substitute the previous stuff in reverse. And it's beautiful. It's a really cool thing. And the best part is, it doesn't matter how big the numbers are. It doesn't matter how big the GCF is. It's always going to have the same basic form. So this is the reason we did the GCD in the first place, is to be able to actually write linear combinations, because those are, we would consider very useful. Any question on this, any part of this? Again, it's a lot of bookkeeping, isn't it? But it's not complicated stuff. Most people, it's not too terrible. Again, have a calculator at your side. Don't do this in your head. It's too dangerous. I only have to make one small arithmetic error and the whole thing, just spirals out of control. Okay, so we are now